Okay, so for problem 6.13, we got this BC, we got C, and we want to find out the first thing, which is the current through the capacitor for time greater than 0. Now, to remember the equation for a capacitor, or the current through the capacitor, it's a differential equation related to the capacitance and the change in voltage across its terminals with respect to time. So, if we have the voltage and how it changes with respect to time, or the voltage, how it changes over time, and we take the derivative with respect to time, then we will get the current through the capacitor. Now, it's just a product rule, nothing complicated. So, I had my calculator do it, and I end up getting, let's see, we have 5, let me just put 5 microfarads for now, times 500, well, over the 500 over here. I get e to the minus 2500 t minus t e to the minus 2500 t, which ends up being ICT 2.5 to the minus 3, 2500 t times 1 minus 2500 t. Now, to find the power, we're still going to use the same formula we've been doing all this time. So we're going to put our expression for the current and the voltage together. And after a little bit of algebra, you'll be able to find that PCT equals 1.25 t e to the minus 5000 t. Oops. Then 1 minus 2500 t. It's just multiplying ICT and VCT. So if we set t equals 100 microseconds, let's go ahead and solve. Okay, so it's 1.25 times 1 minus 6 times e to the minus 5000 times 100 minus 6 times 1 minus 2500 times t so you end up with 56 or 5.68 to the minus 5 watts, which equals approximately 56 microwatts. Now, the next thing is asking, is the capacitor absorbing and delivering power? It is absorbing power at this time. The capacitor is charging. So to find the energy stored, we're going to use another equation. It's just going to be work equals 1/2 of C, the capacitance, times the voltage across the capacitor squared. And since we have an expression for the voltage and everything, let's go ahead and say 1/2 times, or just do 2.5. 2.5 microfarad. Well, it's not really microfarad anymore. and VC is 500 times 100 e minus 6, and it's t, or e to the minus 2500 times 100 e minus 6, that whole quantity squared. So let's go ahead and punch it in. End up with, and the work being about 3.8 nanojoules, or to the minus 9 joules. So now I got to calculate the maximum energy stored in the capacitor and what time that happens. So to do that, we're going to do, this is an optimization problem basically. We're going to take the derivative of the work and set that equal to 0 for the maximum, the inflection point. So dw dt is going to be, let's see, 2.5. It's product rule. I'm just using my calculator for this. End up with an expression where 2 points two times t e to the minus 5,000 t squared times e to the minus 5,000 t. All that equals 0. So let's see. If we set, let's not worry about the exponential, because the exponential is only going to be 0 at 1. Or it's only going to be 0 at infinity. And we don't want that. We want to find the point where there's the maximum. So it's definitely not going to be at infinity, as you can see, because it's discharging towards infinity, I mean. So if we take the other expression right here, let's do factor out the t, 2 minus 5,000. T can't have t0 for the same reason we can't have t infinity. So that means that t is going to equal 2 divided by 5,000 seconds. So 2 divided by 5,000 is 400 microseconds. So that's whenever we're going to have the maximum amount of work. And we can find the energy using our same equation that we did before with the work is 1/2 cv squared. But we're going to plug in 400 instead of 100 in that expression. You end up with the work maximum being 13.5 nanojoules approximately. So it's just all calculus stuff. It's not super hard, it's just pretty tedious. Alright, so we've got a 20 microfarad capacitor, and it's being subjected to these voltage pulses modeled by the equation over the interval of 1 second. So we're going to find out the current pulse for the capacitor through that 1 second interval, and we're going to graph it. So the first thing is we need to evaluate we need to evaluate the current for case 1 or the interval 1. So we're going to have 20 microfarad times 30 times d dt g squared. So remember the power rule for integration or differentiation. It's going to be 2t times 30 times 20 microfarads. So that's 20 times 30 times 2 times, or all divided by 1 million. This looks like 1.2 minus 3 t amperes. And we're going to do the same thing for case 2. So 20 to minus 6 times 30 times d dt of t minus 1 squared. So we're going to do chain rule. Derivative of the inside is 1 times, and that, so 1.2 t minus 1 to minus, let me actually put the exponential in the front. E minus 3 t minus 1 amperes. Okay. So let's go ahead and plot it. We're only over the interval 0 to 1 second. So I'm going to plot these and say at what's 1.2 to minus 3 times 1/2. Let's write this in milliamps just to be a little easier. So 0.6 milliamps. Let's go ahead and draw. Let me do it in a different color. We got a linear function up here, and we have a discontinuity here. Well, it's not actually discontinuous, but let's go ahead and figure out where it starts. So same thing here, 1.2 to minus 3. So 1/2 minus 1 is negative 1/2 of that. So we're going to start down here at negative 0.6 milliamps. And it's going to be the same kind of curve. So I'm going to connect this real quickly. So there we go. We've got a sawtooth wave. It's not actually a sawtooth wave because it's not periodic, but if it was repeating, then it'd be called a sawtooth wave. So there you go. Pretty simple. For 6.20, we've got a 250 nanofarad capacitor, and the capacitor is initially discharged. So we're going to find out what the charge on the plates and the capacitor are at the time t equals 30 microseconds. So the way we're going to do that is we're going to divide this. Well, let me explain the logic first. So a coulomb, or sorry, an amp is a coulomb per second. So if we integrate current with respect to time, we will get charge. So we're going to break it up into 3 regions. We have region 1, region 2, and region 3. The first 2 regions are simple geometric shapes, so we can just use simple rules to find out the charge there. Just do geometric stuff. But I'm going to write out a little table because we're going to do these values in a minute. So ICT is going to be rise and run here, so that's let me write it here. 400 minus 3 divided by 5 minus 6. So that's 80,000 So 80,000 T for time 0 to 5. And then the second one is constant. This is going to be 4 milliamps, or 0.4. Let me do it minus 4. 0.4 milliamps for time 15, or sorry, 5 to 15. And this last one, we're going to have to do something. So the rise of run, we get minus 300 over 30 micro. That's 10,000. And then there's the minus the half from the, because this is a linear function, so it's going to go minus half milliamp. If we extrapolate this from the linear thing. Yeah, because the midpoint would be around here. So that's like minus 250. So yes, this is going to be, let me just do 1 E4 minus 0.5. That's T from 20, I don't know why I wrote 15, to 50. Okay, so if we integrate over these three regions, then we can find the total charge. So Q1 plus Q2 plus Q3 equals Q total, I guess. Let me go ahead and box this off real quick. So Q1 is going to be 1/2 base times height, so 5 microseconds times 0.4. That's going to be 1 microcoulomb. Q2 is going to be 15 microseconds times 0.4. So 0.4 is 15, 6 microcoulombs. Q3, I'm going to use my calculator, integrate the function of, let me just write it down. And it's 24T minus 0.5 ET. That is going to be minus 4.5 microcoulombs. So Q total is going to be 7 minus 4.5, so 2.5 microcoulombs. Okay, so now we can find the voltage on the capacitor. And we can do that by integrating. If we remember, ICT is dV C dt. If we divide by the capacitance and integrate over time, then you get the voltage across the capacitor. So we can do that, or we can use the integration that we've already done. We found the total charge, and just take the total charge and divide it by the capacitance. So we have 2.5 microcoulombs divided by the, what is this, 250 nanofarad, so to minus 9. Let me just leave it as N for now. And a farad is coulomb per volt, so we can get volts this way. 2.5 minus 6 divided by 250 minus 9, you get a voltage of 10 volts as VC. And now you're going to find out how much energy is stored in the capacitor by that current. We're going to go back to the work formula. So work equals 1/2 the capacitance times the voltage squared. So 100 times 1/2, so 50 times 250 times a billion, or divided by a billion is, well, if that's a small number, multiplied by a million, see, okay. I get 12.5 microjoules. And there we go. Not too bad. The only tricky part is deriving the expression for that region. Everything else is cake. So for 6.30, we're going to find the equivalent capacitance between the terminals A and B. I'm going to start out by noticing these two are in series. So adding them together, or adding their inverses together, will give us the equivalent. So 1/48 plus 1/24. That's 1.5/24, so 24 divided by 1.5 is 16 nanofarad. And then the voltages are going to add up. So 30 plus 10 is 40. That's 40. And the new 16 nanofarad is in parallel with the 4 nanofarad. So 20 nanofarad charged to 40 volts. And that's going to be, let me say that it's this is like an equivalent capacitor that has 20 nanofarad and 40 volts across it. So now we've got this capacitor right here in series with that equivalent capacitance. So let me do it in blue. 1/30 plus 1/20 minus 1 is going to be 15 nanofarad. And then 40 plus 20 equals 60 volts. So that new 15 nanofarad is going to be in parallel. Hold on. 30, 20. Yeah, okay. 15 is going to be in parallel with H. Oh, I'm sorry. I did the math wrong in my head. I knew it looked weird. 12, not that. Anyway, so 12 nanofarad is going to be in parallel with the 8 nanofarad. Both going to be charged to 60 volts by the nature of being in parallel. So 20 nanofarad charged to 60 volts. And that's going to be all of these capacitors put together. So we're going to do one more, because I'm going to redraw it. Here's B, here's A. Let me scroll down a little bit, make sure that stays in the frame. So this is 20, 20, and 10. And the voltages we got 5 volts this way, 60 volts this way, and minus 40, or not minus 40, we have 40 volts this way. It is minus 40, but we'll do that at the end. So anyway, not that, I don't need that. We have these all in series, so 1/20 plus 1/20 plus 1/10 minus 1 That's, let's see, 2 over 20, so 110 was 110 is 5 halves, or not 5 halves, 10 over 2, which is 5 nanofarad. Now for the voltage in it, we're going to have minus 40 plus 60 minus 5 equals 15 volts. Now the next part is just the same process. I'm going to start with this far right side and find the equivalent capacitance over here. So these are clearly it's series. So 1 over 36 plus 1 over 18 plus 1 over 12. So let's see, 336 plus 236 is 36 over 30, or 36 over 6, so 6 microfarad. And that 6 microfarad is in parallel with the 24. So 24 plus 6 is 30 microfarad. Oh, I almost forgot the voltages. First one, we have 5 volts, then minus 2 volts, and minus 8 volts. So the whole network is charged at minus 5 volts, and minus 5 volts is shared across the 24 and the 6. So I'm going to do this one right here also. These two are in parallel, so 25 plus 5 is 30 microfarad. We already know they share the same voltage, so 10 volts. So now we got a new simplified circuit. Let's go ahead and write it out. Here is 30 microfarad plus 10, 30 microfarad, and I'll have minus 5. And the last one's 20, I think. Yeah, 20 volts and 30 microfarad. Okay, so these are all going to add up in series. 1 over 30 times 3 equals 10 microfarad. And then 10 minus 5 plus 20 is 25 volt DC. So if we wanted to write an equivalent capacitor, we could say that we had a 10 microfarad capacitor with 25 volts DC charged across it as the starting point. And there we go. So this one's actually a little bit easier than this one, I think, just because it doesn't have that cross plane and the deal going on. For 7.21, we got a couple things to do. The first one is going to find the initial voltage drop across the capacitor. So basically we're going to find out what it's like if this part of the circuit over here is not connected. So to do that, we're just going to redraw the circuit. Put the 10K here. And here's our capacitor. $150 volts, 10 kilo ohms, and then 40 nanofarad. So we're looking for VC 0 minus basically. Well, if the switch has been left in the left position for a long time, that means that the circuit's already reached its steady state, which means that the current flowing through the capacitor is going to be 0. Since there's only one current in the circuit, that means that the current through the resistor is also 0, which means the voltage drop across it is also 0, and that VC 0 minus, or our initial voltage, is 150 volts. So now we want to find out the initial energy stored. We're going to use this formula. Punch in 1/2 times 40 nanofarad times the voltage and the initial voltage squared, which is going to be 450 microjoules. Assuming I didn't make a mistake. And now we're going to find the time constant. So the time constant is tau. It's R times C. So we're going to find the R equivalent and the C equivalent and use that to find out the time constant. So if we redraw the circuit after time equals 0 minus, after the switch is thrown, we have the 5 kilo ohm resistor connected here. And then these two, the 30K and the 60K in parallel, all connected together, 30K, 60K, 5K. And we still have that initial voltage, VC0 minus. We're not worried about that just yet. So, whenever you're looking at the R equivalent, we're going to think about, okay, here's A, here's B. What's the resistance between those two terminals seen by the capacitor? Well, the way that works is just like we've done before. There's two of these resistors in parallel, and then that parallel combination is in series with the other one. So to find the R equivalent, it's going to be 5K plus 30K in parallel with 60K, which is going to be 25K. And since there's only one capacitor in the circuit, C equivalent is going to be 40 nanofarad. So tau is going to be, let me scroll down, make sure that's in the video. Tau is going to be C equivalent times R equivalent, so 25 kilo ohms times 40 nanofarad is 1 millisecond, or 0.0001 seconds. So now we got to find the expression for the capacitor voltage Vt at time greater than 0. There's a couple ways that we can do this, but since we already found the R equivalent, I'm going to redraw the circuit and we'll analyze it that way. So I'm going to have a resistor in series with this capacitor. And it's going to be charged to the initial voltage of 150. Still have the 40 nanofarad. And this is going to be our R equivalent, so I'll put 25 kilo ohms. That's the effective resistance seen by this capacitor. So we have one current in the circuit, we'll call it ICT. Go ahead and write out, maybe a little bit more space, hold on. This will be the next problem. Okay, we're going to go ahead and write out, we only have one KCL, so I'm not going to bother with that. I'm going to write out our equations. So we have ICT is equal to the capacitance times the change in voltage over time. And ICT is going to be VCT over R, which is 25K. And go ahead and put the 40 nanofarad in there too. It may be helpful for you to leave these as symbols if they're big values like this or very small values like this. Practical capacitors have very small capacitance values because a coulomb is such a large amount of charge. Anyway, 40 nanofarad times VCT dt. We're going to set them equal to each other. So 40 nanofarad dV t dt equals VCT over 25 kiloohms. And if we put it into the standard form that's up here, we can find out the rest of this pretty easily. So we're going to try and put this into the standard form. There ends up not being a k here, or rather k is 0, because we don't have anything. There's no like 5 or whatever sitting around here. So we're going to divide both sides by 40 nanofarad, which is going to end up being the time constant. So let's go ahead and put it in terms of, let's put it all on the same side too. So dVct dt minus VCT over tau, which is RC, equals 0. And we know tau is 0.001. So now we can find out what the initial and final voltages are. We know the initial voltage because we calculated it. It is VC0 is 150 volts. We can calculate VC infinity if we take K times tau. Now K is 0, so that means that VC infinity is 0. And our expression for the voltage is going to be VCT equals V infinity, which is 0, plus Y0, or V0, which is 150, times, or minus C infinity, which is also 0, times e to the minus t over tau, and tau is known to be 0.001. So VCT is going to be 150 volts times this exponential decay, which is minus 1000 t. Okay, so for 7.24, we're going to continue using that same kind of technique to find out what the voltage for this capacitor is over time from 0 onward. Now, first thing we're going to do is we're going to consider the initial condition. So this will be our VC0 minus before this switch is closed. Now, before the switch is closed, all the current is going into these other parts of the circuit, the resistors and the capacitor. So after that switch is closed, the current is just going to flow through this loop forever, because this is 0 ohms basically. There's no voltage drop, there's no current flowing through those resistors. So that means that to find the initial condition, we're going to consider the circuit with the switch open. And whenever the switch is closed, it basically makes the current source go away. And we'll see that in a second. So I'm going to redraw the circuit. I can say here is 40 nanofarad. This is 10 kilo ohms, 60 kilo ohms, and 20 kilo ohms, and 20 milliamps right here. So if we want to find VC0 minus, I label the circuit. Here's our nodes. I'm going to call this ground. Let me make sure that I put the plus and the minus, because those are important. Call this V1, call this VC. Now, since we're at the steady state, because the switch has been open for a long time, everything's calmed down. That means that the capacitor is fully charged, which means the current flowing through it is pretty much 0. There's a small leakage current in a practical capacitor, but here it's 0 always. which means that the current through this resistor is also 0, which implies that Vc equals V1. So if we can find out the voltage drop across these two resistors, then we're in business. And to do that, we can either do the whole KCL, EFC stuff, split the currents, or we can just do an equivalent resistance and do Ohm's law. So I'm going to do that. So we have 20 kilo ohms parallel with 60 kilo ohms, which is going to be 15 kilo ohms. So V equals I times R. I'll say that V1 equals 20 milliamps times 15 kilo ohms. The K and M are going to cancel. It's going to be 20 times 15, which is 300 volts. So that is Vc 0 minus our initial voltage across the capacitor. So now we're going to consider the case where the switch closes. Now remember, after the switch closes, all the current, or the voltage drop across these resistors is going to be 0, at least with respect to the current source. So it's just going to discharge the capacitor. The 20 milliamp source goes away, so to speak. So for t greater than or equal to 0, we're going to redraw the circuit with the switch closed so the current source will go away. I'm going to leave the equivalent resistance. Well, I'll redraw the whole circuit actually, and we'll do the equivalent resistance again. Okay, so now we have this circuit. Here's a 60K, here's a 20K, and here's a 10K, here's 48N, and Vc 0 minus, or Vc 0 is going to be 300 volts. Okay, so now we have our circuit, and there's no independent sources here. The capacitor is charged, so it's going to discharge into into this network. So I'm going to find our equivalent for this whole network. We already kind of did, but we want to do that so we can find the time constant. So we have 10K in series with the 15K equivalent, which is the, let me go ahead and just write it out. The 20K in parallel with the 60K. That's going to be 10 plus 15, so 25K. And there's only one C, so 40 nanofarad. So tau is going to be these two together. So 40 nanofarad times 25 kilo ohms is going to be 0.001 seconds, or 1 millisecond, 1,000th of a second. So now we can go ahead and set up an equation to find the infinity, because we know Vc 0, we know tau, we just need Vc infinity. So to do that, I'm going to use my new equivalent circuit that we just made. I'm going to say, hold on, my pen's not working. Give me 1 second, I'll be right back. Okay, so we're going to use our new equivalent resistance to create this little loop right here. And when it creates this little loop, it becomes a lot simpler than analyzing all of these things together. So we're going to have our R equivalent of 25K and our C equivalent of 40 nanofarad. Still have the initial condition, 300 volts plus minus. And we have the current of the capacitor, which is the same current through this whole circuit. So we're going to write out our equations for the components. ICT is going to be 40 nanofarad, oops, not milli, nanofarad, times dVct dt. And also Ohm's law, it's going to be VCT divided by R equivalent, which is 25K. So we're going to set these equal to each other. 40 nanofarad dVc dt equals VCT over 25K. So we're going to divide both sides by 40 nanofarad, and I'm going to subtract this to the other side. So we just have it in our standard form. So dVCT dt minus VCT over tau equals K. Now this equals 0. I'll just write that in, and I'll write that these are tau and K. So here's 0.001. Okay. So remember that this is tau, it's the RC time constant, and this is K. So to find VC infinity, which is what we needed to find the rest of our expression, it's going to be K times tau, which is 0 volts. So the voltage across the capacitor is going to be the infinity plus the initial condition, which is 300 volts, minus the infinity, e to the minus t over tau. So that's going to be VCT is 300 e to the minus 1000 t. And that'll model the behavior for the discharge curve of this capacitor in this network. This is our answer. Okay, this one is a little bit tricky compared to the last one. So the first thing we want to do is find out what I1 0 minus and I2 0 minus are, and then find them at 0 plus. Now what that means is that the instant before the switch is closed and the instant after the switch is closed. So once we do that, we're going to find out the current over time, basically, for the whole for these currents in the circuit. The way we're going to do that is we're going to first look at the steady state. So the switch has been open for a long time, which means that this capacitor over here has been fully charged. And that means that the current going through it goes to 0. There's a very small leakage current that we can ignore. And now we just have one current flowing through all these resistors. And because of that, I go ahead and I went ahead and simplified the circuit, went in and added up those resistors. 5 plus 2 plus 3 is 10. And came up with these equations that will model that circuit. And we're going to go ahead and solve them to find out what the I2 0 minus, or 0 minus for I1 and I2. And we also need to find the initial charge on the capacitor for the next steps. So let's go ahead and I'll use the second KCL, 1 minus V1t over 20 plus 100 milliamps equals I1t, so that is, or sorry, I2t, which is V1t over 20. I should actually say that it's 0. Let's just leave it as V1 for now. This is 0 minus. So multiply everything, not 20. This is 10. Multiply everything by 20. That becomes 1 minus V1 plus 2 equals 2V1. Move the V1 to the other side, divide by 3. So V1 equals 3 divided by 3, which equals 1 volt. So if V1 equals 1 volt, I0 t, or I0 0 minus is 1 minus 1 over 20, which is 0. And if you use our KCL up here, if I0 goes to 0, that means that I2 equals 100 milliamps and I2 equals I1. So that means that I1 0 minus equals I2 0 plus, or not 0 plus, sorry. I2 0 minus, they both equal 100 milliamps. So using that information, we can find the initial charge on the capacitor using Ohm's law, because the current through the resistor voltage drop is proportional to it. So we're going to have 0.1 times 2, and that's going to be 0.2 volts as the VC 0 minus for the capacitor. So now we have I1 0 minus and I2 0 plus minus. Let's go find the plus. This is the instant right after the switch is closed. So since we know that the capacitor voltage cannot change instantaneously, then we have 0.2 volts over here. But current through a resistor can change instantaneously. It has no reactance. So we're going to go ahead and say that I should actually write, this is a minus sign right here. So I went ahead and I combined, since I2 and I3 are the same current, I combined the resistances because they're in series. And if we have 0 minus, or rather, 0 minus VC 0 plus, then that's going to be minus 0 plus. So that's where that comes from. Anyway, we can say that I2 0 plus is equal to minus 0.2 volts divided by 8 ohms, which is 25 milliamps. Or sorry, minus 25 milliamps. So it's quite opposite. And that makes sense because if we have 0.2 volts over here and then 0 volts over here and the current goes this way, that makes physical sense. Everything is working. It's all good. So to find I1 0 plus, it's just VC 0 plus. So 0.2 volts divided by 2 ohms, which is 100 milliamps. Now notice that I1 0 minus equals I1 0 plus. That's because the capacitor voltage cannot change instantaneously, but the capacitor will start discharging into the rest of the circuit. And that's why I2, since the resistor current can change instantaneously, there's no dV/dt over here, then the current can change instantaneously, and it does. So that's why these two are true. Now I'll be right back in 1 second. I gotta fix my mouse. Okay, so for the next part of this problem, we're gonna have to consider the time greater than 0, greater than or equal to 0, the entire transient for the discharge of this capacitor. So I went ahead and prepared the circuit. They have the same labels they did before. And the first thing we're going to need to do is we're going to have to figure out the time constant. So to do that, basically took the capacitor out and sort of drew a circuit that showed what the capacitor was seeing in terms of resistance. And we can use that to find out the R equivalent. So the 3 and the 5 are in series, and they're also in parallel with the 2 ohm resistor. That's going to end up being 1.6 ohms. So the C equivalent, there's only one capacitor in the circuit, it's 2 microfarad. So the time constant is going to be 3.2 microseconds. And I'm going to do the 1 over tau real quickly just for later, whenever we do there you go, whenever we do the final expression. So that's just 1 over tau, which is r times c. So now we can go ahead and start to put everything into the standard form. We need to use our pre-made solution, so to speak. So to do that, the first thing I want to do is I want to find an expression for I3 and I2, for V1 actually. Now, just to make my life a little bit easier, I go ahead and notice that these are, oh, I'm not going to notice, I already drew the KCL for it. I2 and I3 are equal. So another way to write I2t would be minus VCT over the 5 plus 3, which is 8. So that'll just make things a little bit simpler later on. I'm going to go ahead and use the second KCL. Now this 1 is supposed to be over here. I don't know why it's not. So I go ahead and write out the expression. ICT is 2 microfarad times VCT, or dVCT dt. There's I1, which is VCT over 2, and that equals minus VCT over 8. So I'm going to go ahead and simplify it, put it all on one side. First thing I want to do, I'm going to divide everything by the c, and also going to add this to the other side. So we're going to be left with, let's see, that's this is 4/8, I think. Yeah, 4/8, so 5/8. So dVCT dt is going to be 5/8 times, oh, I'll just do 5 VCT divided by 8 times 2, or 2 minus 6 equals 0. So let me just think real quickly. If we did 5/8 is how much? Times, or divided by 2 microfarad. Yeah. So I'm going to go ahead and just write it again in a nice way. That's going to become VCT, and then 1 divided by 3.125. And that is actually tau. And that equals 0. Okay, so, or not y, VC infinity is going to equal k times tau. And if you remember, this is tau, and this is k. So 0 times anything is 0. We can find an expression for the voltage across the capacitor with respect to time. Using the solution for a differential equation, if VCT, now and VC infinity is 0, so 0 plus the initial, which is 0.2, VC0 minus is 0.2 volts, and then e to the minus t over tau, so that's going to be 3,12500 T. So that is our expression for the voltage. We can find the current through each of these things using the equations we got drawn up earlier. So I'm going to do I1T first, which is just VCT over 0. So I1T is going to be VCT divided by 2, which is 0.1 to the minus 3,12500 T. And I2T is going to be VCT over 8, which is 0.025. Yeah, I think that's right. 0.025 e to the minus 3,12500 T. Now, we have the answer, so we're done here. But one thing we can do just to make sure that our answer makes sense, we already calculated that I1. Oh, I actually forgot the minus. There you go. There's a minus there. Very important. So we already calculated that I1 0 plus was 100 milliamps. Well, if you plug in 0 for T, or like very close to 0, just a very small number, this is going to go to 1. And that means that we've confirmed that equals 0.1 amps. We can do the same thing here. Set this to 0 or very close to 0. We're going to end up that I2 0 plus equals minus 0.25 amps. And there we go. It's a little challenging whenever you get these multiple steps, but it's the same logic all the way through. Just be careful. In this one, we've got 2 switches, but they work just like the other switches. It's just that these things are going to shut off both sides of the circuit at the same time, leaving us with this middle section. So I went ahead and wrote out the equations and everything already, but all we really need is to find this VCT. And to do that, we can just put these two in parallel and solve for it. Or we could write everything out, and I'll just do that on the calculator. That'll actually work just the same. So it's kind of a messy math equation here, so I'm going to definitely not write down every step. I know that might be kind of annoying if you can't figure out the algebra part, but really it's just, it would take me 3 pages. So anyway, ICT is going to be 0 at the steady state because the capacitor is fully charged, so it's open, so it's going to be 0. And then I3 ACT plus 120 over 1.8K. Now these numbers are not pretty, so that's why I'm going to go ahead and just use my calculator for this one. It's just one equation, one unknown, lots of decimals and stuff, so go ahead and press that in. I get VCT equals minus 102 volts. So that's, or I should say VC0 minus. This is our initial charge on the capacitor. So using that, we can move forward to the next step, where it's just time greater than 0. Now we just left with the capacitor with its initial charge, and it's discharging to this resistor until it runs out of energy. So I went ahead and wrote out the equations. We're going to set ICT to equal ICT. So 10/3 to minus 6 dVc T dt equals negative VCT over 12K. And the reason why it's negative is because I drew the current going this direction. And I did that because the current through the capacitor is determined by this derivative. So it doesn't change anything. And I wanted to basically make it so that way when I add this to the other side, it becomes plus and gets in our standard form. So if I divide both sides by 10 thirds microfarads, then we're going to have a final expression that looks like this. dVC t dt plus VCT divided by 1 over 25, which is our time constant, tau. It's also 0.04 if you get that in the calculator. And then this is 0 on the other side. So based on that, we can find that VC infinity is going to be k times tau, which is 0 in this case. So we can write our final expression for the voltage across the capacitor. It's going to be the voltage at infinity, which is 0, and then the voltage at the initial state minus the voltage at infinity. So that's minus 102 minus 0, e to the minus t over tau, and tau is 1 over 25, so it's going to become 25t. And that models the voltage across the capacitor here. Now the problem asks for how many microjoules of energy are dissipated in the 12 kilo ohm resistor after 12 milliseconds. Well, we can figure that out using an integral. You may remember from physics that a watt is a joule per second. So if we integrate the power, then we're going to get the energy. So going to take we're going to use v squared over r because the current's going to change with the voltage. So 102 e to the minus 25 t over 12 kilo ohms. Don't forget the square. So this is going to be, what's 102 squared? 1004 or something. So that's going to be 0.867 E, and we're going to have the 2 go inside, so it's going to become minus 50t, just to exponent rule. And then if we integrate this, e to the minus 50t BC, I'm going to have t equals 12 milliseconds, like the problem asks. Going to get an antiderivative, it's just 0.867, 1 over 50 e to the minus 50 t, and we're going to have 0.0120. So I'm going to do this real quickly. Actually, this is minus, I think. Yeah, it's minus. So let me do this math real quick. We're going to get the energy in joules. So I get 7.82, I was round up to 4, 7.8236 millijoules, which is going to be just divided by 1,000, or multiplied by 1,000, I guess. Yeah, multiply by 1,000, and then pull that 1,000 into the exponent, and we get 7. Let me get rid of the dot. We get 7824 microjoules. Okay, so we got the first part of the problem. Now I'm going to find out how much time it takes for the resistor to dissipate 75% of the power or not the power, the energy stored in the capacitor. So to do that, first, I'll come back to this integral business in a moment. So the first thing we need to do is we got to find out how much energy is in the capacitor. So the energy in the capacitor is going to be 1/2 C V C 0 minus squared. Let me put that around there. There you go. So we know C is 10/3, so it's going to become 5/3 times, or divided by 1,000,000. So 5/3,000,000 times 102 squared. So 104. Let me do that one more time. 1/2 times 10/3. Okay, so I get 0.01734 joules. So that's how much energy is stored in the capacitor after it's been fully charged. So now we're going to find out how much time it takes to basically for the resistor to do its job. So first thing I want to do is I want to find out what 75% of this number is. So that times, actually I have it written down already. So that times 0.75 is 0.013 joules approximately. Okay, so now we're going to work kind of in reverse. We already have, I think, an expression, for the work. So if we integrate and then find the anti-log, we should be able to find the answer. So I'm going to have 0.867 e to the minus 50t and the dt. It's going to equal 0.013 joules whenever t0 equals what we're looking for. So we're looking for that. So I'll do the antiderivative and then do the anti-log basically. So let's see, 8.67, blah, blah. I think I actually have it up there, but let's do 0.867 times 50 and end up with, let's see. So these numbers on the outside actually cancel out if I set them equal. That might make it a little bit easier to understand. So 0.75 times the 0.01734. Well, if you take the 867 blah 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 and divide it by this, we get the same number. So 0.867 divided by 50 is going to be 0.01734. So these are going to cancel out, and we're just going to be left with the antiderivative. And we can say it's 1 minus e to the minus 50t. Oops. Minus 50t equals 0.75. So move forward. I'm going to put the e on the other side and subtract. So I get 1 minus, I'll just say it's a quarter. So 0.25 equals e to the minus 50t. I'm going to take the log both sides. So the ln of 0.25 is going to equal minus 50t. So ln of 0.25 divided by negative 50, I get t equals 2.77. No, not 2.77. 27.7. 27.7 milliseconds. Okay. So yeah, it's just a bit of calculus heavy in this problem, but the analysis isn't too bad. It's just, you can even use a voltage divider if you wanted to find the AC0 minus. In 7.29, we've got this switch right here. And that moves from position 1 to position 2 at time equals 0. And before then, it has been there for a long time in position 1. So we can assume that at a steady state, or that the circuit is in the steady state before that. So that means that the current through the capacitor at time equals 0 minus, which is the time just before the switch is thrown. The current through the capacitor is 0. Since there's only one path through the current, all the other currents have to be 0, which means that this dependent voltage source is going to go to 0. The voltage drop across the resistor is going to become 0. And that means that VC 0 minus is 15 volts. Not too bad. So now we're going to consider the case when the switch is thrown, which is t equals 0, or greater than or equal to 0. I went ahead and drew the circuit already. Don't be confused about this minus sign. I put the arrow this way because it would make the analysis a little bit easier. And the current directions are arbitrary, so I just went ahead and said that. But before we can do that, we need to say that, or we need to find out that we need an expression for V1 in terms of VCT. We actually have an expression that we have right for free, goes the dependent source. So 5 times I0 is going to be minus 5, or minus V1 over 15 times 5 equals V1T minus VCT. So if we multiply this out, it's going to become minus 1/3. And I'll just move it to the other side, so it'll become, not minus 1/3. Or is it? 5 over 15? Yeah, minus 1/3. Minus 1/3, and I'll move it to the other side, so it'll become plus. So VCT equals 4/3 of V1T. So if we want to find V1 in terms of VCT, we just divide. So 3/4 of VCT equals V1T. That might be cut off. I'll scroll in a second. So yeah, we just flip the fraction. So now we can substitute in, we're going to set I0 to equal I0. So I believe it's 2 microfarad dVCT dt equals minus V1, which is minus 3/4. So minus 3/4 V1 or VCT over 15 ohms. So that's going to become, let's see, minus 3 over 60 is minus 120. So I'm going to go ahead and move to the other side and then divide by the capacitor value. just to get it in our standard form so we can use that kind of expression. This is going to become, see, 1 over 20 divided by 2 million, or not divided by 2 million, sorry. 1 over 20 divided by 2 millionths is 25,000. So we're going to have time constant of 25,000, or 1 over 25,000. VCT equals 0. So VC infinity is going to be K times tau. K is 0, so it's going to be 0 volts. VCT is going to be the initial, or the infinite, so it's 0, then 15 minus 0, so 15 e to the minus 25,000 t. And the question asks for IoT. Well, to find IoT, we're just going to do Ohm's law. So IoT equals VCT divided by 15 ohms. Actually, no, we need the equivalent resistance in the circuit, not the resistor. Actually, yes, we get that over, yeah, the equivalent resistance in the circuit. And we can find that because we know the time constant. So REQ times C. So I'm going to do 25, or 1 over 25,000 times, or divided by C, so 2 minus 6. That's going to be 20. So the R equivalent is 20 ohms. So that's going to be a quarter e to the minus 25,000 t amperes. So that was not too bad, especially compared to some of the other ones. But yeah, just got to remember to be careful with dependent sources. Alright, so this last one is a two-parter. The assignment says 7.31 is the last problem, but it requires the work from 7.30. So I went ahead and did a bit of work. But basically, the switch has been in this position for a long time, and it moves to position Y at time equals 0. So first thing I want to do is I want to find the steady state. And to do that, we're going to, well, before I get to that, the first part is to find alpha, which is a unknown quantity in the circuit, such that the time constant is 40 milliseconds. So if the time constant is 40 milliseconds, that means REQ times CEQ has to equal 40 milliseconds, right? So if we know what the C equivalent is going to be, because there's only one capacitor in the circuit, we can find our equivalent using a ratio, and that ends up being 50 kiloohms. So we're going to need that later when we're looking for alpha. So to find VC0 minus is really simple. Current through this is going to be 0 at the steady state. So that means all the current is going through that resistor. So the voltage drop across is proportional to the current times the resistance, Ohm's law. So 5 milliamps times 3.6 kiloohms is going to be, the K and the M are going to cancel, so 5 times 3.6 is 18. So VC0 minus is 18 volts. All right. So now we've got to do a bit of, we have to find sort of like a Thevenin equivalent, if you want to call it that, for the circuit. Okay, and to do that, I went ahead and put in a test source. I went and chose a 1 amp test source because it just made the numbers a little bit easier. But anyway, so if we have the 1 amp test source right here, that means that the current through this resistor is 1 amp. And since we set this to be 0 over here, then VA or VA delta is equal to 1 amp as whatever the current is times this. So that ends up being 5,000 volts. And that sounds like a lot, but it's just a test. This is just a test current. It takes a lot of energy to move an amp of current through the circuit because of these high resistance values. Anyway, so that means if we set all this up, alpha times V delta, which we determined to be 5,000 plus 1 is equal to I1. I'm going to multiply both sides by 20,000, so that's 5,000 times 20,000. That is a big number. It's like 100 million. So I'll say 1 E8 alpha plus 20,000 equals VT minus 5,000. All right, so if I simplify this out, let's say that 25,000 plus alpha times 100 million equals VT. If we can find VT, then we'll be able to find out what alpha is. So VT is going to be the R equivalent. So if R equivalent is 50 kilo ohms, like we calculated earlier, and IT, the test current, is 1 amp, that means that VT equals 50,000. So if we do 50,000 minus 25,000 divided by 1E8, we should get alpha, unless I made a mistake. Let's see. 25,000 divided by 1E8. I end up with alpha being 250 and minus 6. It's just a amps per volt. This is Siemens. It's just the reciprocal of resistance. Anyway, so now we know alpha. Okay, go ahead and yeah, so now we gotta find V delta. So did I mess up? No, okay. Sorry. So V delta is gonna be proportional to the current flowing through it. So if we can find ICT, once again, like if you go back to the circuit, if we can find ICT, then we'll be able to find out what V delta is using Ohm's law. So I'm going to use the equivalent resistance just to simplify the math a lot. Basically, I'm going to plug our Thevenin equivalent circuit back in, and we'll solve. So there's only one current at ICT, so we'll set them equal to each other. So 0.8 minus 6 dVCT dt equals minus VCT over 50K. So it's going to simplify dv dt plus vct, and we find out what tau is going to be 0.8 e minus 6 times 53. That's going to be 1 over 25 equals 0. So vc infinity is going to be k times tau, which is 0. vc 0, I think was, let's see, 18? 18 volts, yeah. So our expression for the voltage across the capacitor is going to be 18 e to the minus 25t. And we can use that to find ICT. So ICT is going to be not blue. ICT is going to be VCT over REQ. And REQ is 50K. So we're going to 18 over 50K e to the minus 25t. And we'll have an expression for that. So 18 divided by 50,000. I multiply that. So 360 microamps is the maximum current, and then e to the minus 25t. That is ICT. So using ICT, we can find out what V delta is with respect to time, because V delta is going to be ICT times 5K, I believe. Right? 5K. Okay. So if we multiply this by 5K, end up with V delta being 1.8 volts maximum, and then 25T. And that is our answer. Now that makes sense because the R equivalent is 50 kilo ohms. And the resistor that the voltage V delta is across is 5 kilo ohms. So it makes sense that it would be 10 times smaller for the same amount of current. So yeah, not too bad. We're going to move on to the next part. So now we got to find out how many microjoules of energy are generated by the dependent source during the time that the capacitor is discharging. So to do that, we need to find the voltage drop across it, and we already have the current flowing through it. So we're going to go ahead and do the power equation. So 648 to the minus 6 e to the minus 25t as I times v, which is going to be vs. It's the drop across it. So, oh, actually, I did it the opposite direction here. I might have to do it like this. Bigger voltage on this side. So I was going to make this opposite. So let's see, 16.2 e to the minus 25t. So let's go ahead and put this together. So 648 minus 6 times 16.2. I get minus 0.01049. And the exponents are going to combine. So it's going to become minus 50t. That's going to be the power with respect to time supplied by the dependent source in watts. So to find the energy, we're just going to integrate it. So work is going to be, says during the time the capacitor charges, or yeah, during the time the capacitor discharges. So that could be any number. I'll say infinity. It usually takes about 5 time constants, but just to be safe, we'll do infinity. 0, 1. I'll round that. E to the minus 50 t dt. It's going to be, let's see, this divided by 50 is what? So 210-ish minus 6 is going to be minus e to the minus 50t. Right? Yeah, so the minus signs are going to cancel. I think. Yeah, so it's going to become plus. That's going to be from infinity to 0. So that means that the work is 210 microjoules. Since at infinity it's going to be 0, and at 0 it is 1. Okay, so now we're going to have to find the total energy stored in the capacitor circuit and total energy dissipated. Okay, so the capacitor is charged to a 18 volts as VC0 minus. So 1/2 of, was it 0.8? Forgot to copy the value. 0.8 microfarad. And 18 squared. So that is 0.4 microfarad times 18 squared, which is times this is 129.6 microjoules. So there must be a mistake here. Actually, no, it's being delivered to 210. So that makes sense. Okay. So that means that the resistors have to make up the rest of the power dissipation, or they have to make up all of the power dissipation, I should say, because both of these are supplying energy. So we're going to find the power for the 5K resistor. 5K resistor is going to be 1.8 e to the minus 25t, I think. Yeah, 1.8 minus 25t squared divided by 5,000. So 1.8 squared, 3.24 divided by 5,000 times a million, just to make it a bigger number. 648 e to the minus 50 t, and that will be watts. So, or not watts, microwatts. That's not a mu. That's a mu. We're going to do a W again too. Okay. So 648 microwatts. If we integrate that, 648 e to the minus 6 divided by 1, or divided by 50, and we're going to get, the antiderivative is just going to be this, and it's 0 to infinity, so infinity 0 That's just going to be that divided by 50. So 12.96 or minus 12.96 microwatts, or microjoules, no, watts. So there's a loss of energy here. Now let's go ahead and do the 20 kilo ohm. So that's 16.2 e to the minus 25t squared divided by 20,000. That's going to be 60.2. I'll multiply this by 1,000. 13.122 minus 3 to the, I'll just go ahead and put it in milli, to the minus 50t milliwatts. Once again, I'm going to do the integral. So 13.322 divided by negative 50 e to the minus 50, infinity is 0. So infinity is that, and we're going to have zero 0.26244 millijoules. So that'd be a 200. I'll just go ahead and do this again. It's going to be 262.44 microjoules. Okay, so let's go ahead and add these all up. 262.44 plus 12.96, 275. Now these don't end up equaling 0, I can tell right away. And I don't think I made a mistake in here, so there must be a problem with this question, because there's no other way for these currents and voltages to be physically possible, so I'm not sure what happened with this problem. Sorry guys.